Okay, guys, so in the Stoich sample problems, there were only 9 problems that you had to work out. What I'm going to do in this little lecture is go over the ones that I worked out for you in that PowerPoint that most of you looked at, and then I'm going to go ahead and work through the sample problems that I gave you that you had to work out yourself. So what I want you doing with this, to kind of show me that you were following along and you're grasping the concept a bit more, when I go to work out the problems that you should have worked out on the sample problems worksheet and then turn that in for a grade, what I want you doing is just writing all the problems down on a piece of paper. They can all be on the same paper. It might take front and back of a paper. That's about what it took me, but and then I'm going to have you take a picture of the paper and turn that in as one of your grades for this week, because I just want to know that you watched this video, you were kind of following along. So, and I'll try to remind you when I go to work out a problem, you should be working it along with me, literally just copying down what I'm putting, and then I'll have you calculate the problem on your own, okay? But first, I just wanted to kind of talk through the PowerPoint. So stoichiometry is a bit different than what we have been doing in that we are working with actual chemical reactions. So stoichiometry is different than just molar conversions because stoichiometry actually considers how much of a product or a reactant you need or will produce. And I mean, if you think about it, like that's important in chemistry labs if you're trying to figure out like the most efficient way to produce, a product for consumers. You have to realize like how much you need and how much you get out from what you have. So that's kind of where stoichiometry comes into play, just so chemists know what they need and how much of it they need or how much they're going to get, right? You don't want to be surprised at the end of a chemical reaction. So lots of times they'll use stoichiometry to be like, okay, this is what I have as a reactant, and this is what I know it's going to produce because we know how to produce the product or how to predict the products. So then you can predict how much of a product you'll get, and then if you got that product, then everything went fine, and if you didn't, then something was off either in your calculations or you actually performing the experiment. But that's kind of where stoichiometry is coming from and why, as chemists, we do it. So the big thing with stoichiometry is that you have to work with balanced equations. Remember, we learned how to do balanced equations, and balanced equations are important because if we just had H2 plus O2 yields H2O, it would look like an atom of oxygen disappeared in the reaction. But we know through the law of conservation of matter that nothing can be created nor destroyed. So this is where balanced equations come into play, because we know we need 2 atoms of H2 and just 1 oxygen, and then we'll get 2 water molecules in the end. And if I were to just read what this chemical equation is saying, for every 2 moles of H2, 1 mole of oxygen is needed, because remember there's an imaginary 1 there, to produce 2 moles of water. Okay, so this number, this coefficient in the front is telling you how many moles of something you have. So again, if it's blank, imaginary 1, we only need 1 mole of oxygen gas. So on this first example, we're just balancing the equation, which we already did. Boop. I just put a blank there so you know that that's an imaginary 1. So the question says if 4.2 moles of hydrogen gas reacts completely with oxygen gas, how many moles of oxygen are needed? So it says how many moles. So first, we're going to make sure the equation is balanced. Sometimes it is, sometimes it isn't. We're going to make sure we have 4 hydrogens, 2 oxygens, 2 oxygens. So we're good there. And then we're going to identify our given and our unknown. So our given is what is given to us. It's the information that's given to us in the problem. So our given for this problem is 4.2 moles of H2. Got to remember that of H2 part because that's telling us moles of what. And then our unknown is what we're trying to find as chemists or as, researchers, what we're trying to find. And what we're trying to find is how many moles of O2 are needed. And then third step, figure out how to set a problem and then plug in numbers. Okay? So remember that we always start with our given in the top little box, whatever you want to call it. So we have 4.2 moles H2. And don't even worry about the numbers at first. If we have moles of H2 on top, we need moles of H2 on bottom. And then we're trying to get to moles of oxygen. So can we go from moles to moles of something else? Yes, we can. So we'd have moles of O2 on top. And then we are to what we want. So let me erase all this. And to figure out how many moles of H2 equal how many moles of O2, how we figure out that conversion factor, we have to look back up here. So there are 2 moles of H2 for every 1 mole of oxygen. So there'd be a 2 down here. 2 moles of H2 is equal to 1 mole of O2. And then we'd work it out like normal. So you'd multiply everything across the top and get 4.2. And multiply everything across the bottom and you get 2. And then you divide to get, I shouldn't have needed a calculator for that. Then you get 2.1 moles O2. And that is your answer. Okay? So let's try it again with a different problem. This one is a real life scenario problem type. It says, in a spacecraft, the carbon dioxide exhaled by astronauts can be removed because it needs to be removed because we can get carbon dioxide poisoning. It can be removed by its reaction with lithium hydroxide, which is LiOH, according to the following chemical reaction. Okay, great. We have CO2 plus 2 lithium hydroxides yields Li2CO3 plus H2O. Okay, so the question says, how many moles of lithium hydroxide, are required to react with 20 moles of carbon dioxide, which is the average amount exhaled by a person each day. So, is the equation balanced? We have 1 carbon. We have 2 oxygens. Oh, no, we don't. We have 2 right here plus the 2 right here, so 4. We have 1, 2, 3, 4. We have 1, 2 lithium, so we have 2 lithiums here. We have 2 hydrogens, and we have 2 hydrogens here. So yes, the equation is balanced. Next, we have to find the given and the unknown. So the given is what is given to us in the problem, which is 20 moles of CO2. That's our given. And the unknown is what we're trying to find, which is moles of lithium hydroxide. Okay? So, obviously, remember, we start with our given, and then our unknown is what we end up with at the end, is what unit we need to end up with. Okay? So, you set up the problem like normal. Your given was 20 moles of CO2. If you have moles of CO2 on top, you have moles of CO2 on the bottom. We're trying to get to moles of lithium hydroxide, and you can go from moles to moles, okay? But remember, you don't have to fill in the numbers yet. But to get those numbers, you have to look at the balanced equation. And for every 1 mole of CO2, you need 2 moles of lithium hydroxide. Do your math, so multiply everything across the top and get 40. Divided by 1 is 40 moles of lithium hydroxide. So really, a lot of this is what we did with molar conversions and dimensional analysis, all of that, but we're just adding in the moles from the balanced equation. That's really the only thing that's different here. Okay, so sample problem 2 is the first one I made you work out on your own. So if you want a grade, or you're just trying to make me happy and do what I'm assigning, then you can start with this problem here. Literally just write them all on a sheet of paper. Scratch paper, you know how much I love scratch paper. Just, they can all be on the same paper, just number them, it'll be fine. And then you'll just turn that in to show me that you watched this video and followed along and tried to learn something. Okay, thanks. So, sample problem 2 says, ammonia, NH3, is widely used as a fertilizer and as an ingredient in many household cleaners, which is true. And there's ammonia is in most cleaners. How many moles of ammonia, I'm going to underline that because that seems important, hint, hint. How many moles of ammonia are produced when 6 moles of hydrogen gas react with an excess of nitrogen gas? So the excess part doesn't really tell us a whole bunch. That's just saying like, hey, don't worry about it. Kind of, you have enough. So here's the equation. I gave it to you here. In the future, on some of the problems, you will have to figure out the equation on your own or just follow along with me. So this is your equation. We need to balance it first. And so let's see. We have 2 hydrogens over here, and we have 3 right here. So there's no number that I can multiply 2 by to get 3. So then you have to use like the least common denominator. And so we know that we'll have 3 H2 plus that. I haven't figured that out yet. What we need there, H3. So since we have 6 here now, let's put a 2 here to try to see if that works. Yippee-ki-yay, we have 2 nitrogens here, 2 nitrogens there. The equation is balanced. So then it wants us to find the given and the unknown. The given is what is given to us in the problem, which is 6 moles of hydrogen gas. And then the unknown is what we're trying to find, which is how many moles of ammonia. So we're going to set up the problem with our given up here, 6 moles. And this is where you start writing. Literally anything starting down here that I write, you should be writing. 6 moles of hydrogen gas. And if we have moles up there, we have moles down here, moles of H2 to be specific. And then next thing I'm going to do, I'm going to look and try to figure out what are we getting to, which is moles of ammonia. Can I go from moles of H2 to moles of ammonia? Yeah, I can. So I will do that. Okay. And then to figure out the conversion rate between moles of H2 and moles of ammonia, I look back at the balanced equation. If I looked up here, literally everything's 1, so that doesn't matter. You got to look at the balanced equation. So there are 3 moles of H2 and 2 moles of NH3. So now you multiply everything across the top and everything across the bottom. And I trust that you can work this out on your own. So I'm going to leave that as part of your assignment, is to figure out the answer and write it in that box. This one shouldn't be hard because it's 6 times 2 divided by 3. So, hello. Don't forget about your unit, which is going to be moles of ammonia, which is what we wanted in our unknown. Yay. If you are like, well, I don't even have like a scientific calculator. If you turn your iPhone sideways, it's scientific, but you really don't even need a scientific calculator. Literally, the cheapest calculator will work for this. Your brain could even work for this, but I digress. Okay, so for you turning in the assignment, make sure you have at least the balanced equation, this part that I have worked out, and then you will work out the answer with the correct units. Okay? And moving on to the next one. This one, I was really challenging you because I'm making you write the equation. But I picked a relatively easy one that you should all know how to do. So sample problem 3, the Next one you're writing on your assignment paper says the decomposition of potassium chlorate, and then I tell you what potassium chloride is, into potassium chloride and oxygen gas is used as a source of oxygen in the laboratory. How many moles of potassium chlorate, important, are needed to produce 15 moles of oxygen gas? Okay, so first things first, we have to write our equation. It says the decomposition, and I hope we remember that the decomposition means it starts as one reactant and then decomposes into two products. So we have ClO3 yields potassium chloride plus oxygen gas. But are we done? No, because then we have to balance the equation. So here I have one potassium, one chlorine, but those oxygens are going to throw us off. Again, we have to use the least common denominator. So I'm going to throw a 2 there and a 3 here so that I have 6 oxygens, and then easily I can throw a 2 in front there, and then it's balanced. Next, you need to find the given and the unknown. Here, I already have them underlined. That's our given. And this right here, where it's asking us, is the unknown. Then we're going to set up the problem. Let's use pink, because it's my favorite color. Okay, so we start with our given, which is 15 mole of oxygen gas. Don't forget that, because oxygen gas, or oxygen is a diatomic element, so you know. And if we have moles of O2 on top, we have moles of O2 on bottom. Don't even try to fill in a number yet, because you literally cannot, because we don't have anything on top, so you don't know what you're trying to convert to. So therefore you can't know a conversion factor. So just fill in the units first, and then we go back later. And what are we trying to get to? Moles of potassium chlorate. We can go from moles of something to moles of something else. And potassium chlorate is ClO3. Great. And that's the last step. Let's look back at our balanced equation. For every, moles of O2 is 3. And then we have 2 moles of potassium chlorate. Okay? Our units cancel. And we're left with the unit that we want, which is moles of potassium chlorate. So don't forget that when you answer it on your own. So when you turn this paper in, I want to see the answer worked out. But again, this one you can do in your head. Okay? Okay, sample problems 4 and 5 I did work out for you. So I'm just going to go over the first one because it does get a bit trickier. So sample problem 4 says, in photosynthesis, plants use energy from the sun to produce glucose and oxygen from the reaction of carbon dioxide and water. What mass in grams of glucose? Ooh, that seems important. Mass in grams of glucose is produced when 3 moles of water react with carbon dioxide. So first things first, you have to start with the balanced equation. So the reaction, even if you did not remember what photosynthesis was off the top of your head, even though I feel like I drilled it into your brain last year in biology, the basic reaction is CO2 plus H2O plus energy yields C6H12O6 plus O2. But that is not balanced. To balance it, we have to slap a couple 6's in front of things, and then it's balanced. Then we have to find our given and our unknown. Our given, as mentioned in the written problem, is 3 moles of H2O. And our unknown is the mass of glucose produced. Okay, so I just carried the balanced equation over. We're going to start with our given, which is 3 moles of H2O. If we have moles of H2O on top, what do we have on bottom? Moles of H2O. And then we have to think about what we're trying to get to. And we start off with moles of H2O, and we're trying to get to grams of glucose. Can we go from moles of H2O to grams of glucose? No, because we're measuring two completely different molecules. So from moles of H2O, we have to go to moles of glucose, C6H12O6. And then if we have moles of glucose on top, we have moles of glucose on bottom. And now, what are we trying to get to? Grams of glucose. Can we go from moles of glucose to grams of glucose? Yes, because now we're talking about the same thing. Okay, so this is the basic setup. Now we can plug in our numbers, where you have, from our balanced equation, H2O, we have a 6 in front. CO2, we have an imaginary 1. So we need 6 moles of H2O to produce 1 mole of glucose. And then over here, this number right here came from our molar mass. Remember how we find that using the handy-dandy periodic table? So I'll run over how to do this again. Since we have 6 carbons and the atomic mass for 1 carbon is 12, and we have 6 of those, this is carbon, is 12 times 6. Okay. Hydrogen is 1 gram, but we have 12 of them. And then oxygen is 16 grams, but we have 6 of them. So let's do that math. I can do that one. 72. 96. Let's add all these together to get 180. And I round it up or down. Okay, so that's where the grams of glucose came from, is the molar mass. Okay, and then we multiplied everything across the top, everything across the bottom, and then divided and got 90.1 grams of glucose. So let's try it with a different problem. This is sample problem 6. So you should be writing everything that I write down for your assignment. This is let me look. This was only the third problem I had you work out. So you should be starting your third problem now. Okay? So doing basically the same thing, just with different reactions and different numbers. Same principle though. It says when magnesium burns in air, it combines with oxygen to form magnesium oxide, according to the following equation. I was nice and even gave you the balanced equation. Wow, I was feeling real generous here. So we have our balanced equation. Let's check though, because we have 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens. Yeah. The question though is, what mass in grams of magnesium oxide, I'm going to underline that because it seems important, is produced from 2 moles of magnesium? Okay, so since we have our balanced equation already, we can move on to step 2, which is finding the given and the unknown. Here, that is the unknown because it's asking for that, and what it gives us is that. Okay, so then I start with my given up here, 2 moles of magnesium. And if I have moles of magnesium on top, I have moles of magnesium on bottom. And what am I trying to get to? The mass of magnesium oxide. So can I go from moles of just magnesium to grams of magnesium oxide? No, because they're not the same compound. So we're going to have to stair step it a little and go to moles of what we're trying to get to, which is magnesium oxide. And if I have magnesium oxide on the top, moles of magnesium oxide, then I have moles of magnesium oxide on the bottom. And I'm still trying to get to the mass of magnesium oxide. So can I go from moles to grams of magnesium oxide? Yes, I can. Okay. So now let's plug in the numbers. Right here, we have to look at the balanced equation. So moles of magnesium, 2 moles. Moles of magnesium oxide, 2. Okay. Great. That does reduce to 1 to make your math easier. And then for every 1 mole of magnesium oxide, how many grams do we have? We have to consult our handy-dandy periodic table. Magnesium has a mass of 24.3. Let me work that out up here. 24.3. And that's magnesium, and we only have 1. And then oxygen, as we know, is 16. Great. 40.3. Okay. Moles of magnesium cancels. Moles of magnesium oxide cancels. We're left with grams of magnesium oxide. But you need to calculate the final answer. Okay? Moving right along to our next problem, sample problem 7, which you had to work out. So, let's start by reading the problem. It says, what mass of glucose can be produced from a photosynthesis reaction that occurs using 10 moles of CO2? First things first, let's write the reaction. It's talking about photosynthesis, so we know that that is CO2 plus H2O yields C6H12O6 plus O2, balanced 6 over there. Okay, first 2 steps done. Next step, identify the given and the unknown. It's asking for mass of glucose, so that's our unknown. And can be produced from a photosynthesis reaction using 10 moles of CO2. That is our given. So let's start. We have 10 moles. You should be writing this too. 10 moles CO2. If I have 10 moles on, or if I have moles of CO2 on top, I have moles of CO2 on bottom. I'm trying to get to the mass of glucose, so I can't go from moles of CO2 to grams of glucose. So I have to go to moles of glucose, which is C6H12O6. If I have moles of glucose on top, guess what? Okay, and now can I go from moles of glucose to the grams of glucose? Yep. Okay, now let's fill in the numbers. CO2, we have 6 moles for every 1 mole of glucose. And in 1 mole of glucose, we have how many grams? So it's going to be a bigger one because, we already worked it out, didn't we? which problem? We worked it out in a different problem. If carbon is 12 and we have 6 of them, hydrogen is 1 and we have 12 of them, and oxygen is 16 and we have 6 of them, it works out to be 180 grams. Okay? Let's make sure everything cancels. Moles of CO2, moles of CO2, moles of glucose, and we're left with grams of glucose, and you can find the answer by working it out. So make sure you're working it out, multiply, divide, to get the answer for the problem, for how many grams of glucose can be produced. That's what we're trying to find. Okay, so moving on to sample problem number 8. You only had to work out part B, but I am going to go through parts A and B. Okay, so it says the first step in the industrial manufacturing of nitric acid is the catalytic oxidation of ammonia, given this equation. And then the two questions are, it says the reaction is run using 824 grams of ammonia and excess oxygen. And then the first on A, it says how many moles of NO are formed. And then B says how many moles of H2O are formed. So we are going to have to work this out in 2 steps. You can't figure out both of those in the same thing. Okay. So we do have to start with the balanced equation. This one is a bit trickier to balance. While you were trying to balance it, you probably had to put some things down and then erase and then keep going. But it should have ended up being 4 moles of NH3, 5 moles of O2 yields 4 moles of NO, and 6 moles of water. This right here is our given, and these are our 2 unknowns. So this is going to be how you work out part A. So the given for part A is still 824 grams of NH3. If we have grams of NH3 on top, we have grams of NH3 on bottom. And what are we trying to get to? On A, how many moles of NO are formed? So can we go from grams of ammonia to moles of nitric oxide? No. So we have to go to moles of NH3. That's a 3. And then if we have moles of NH3 on top, we have moles of NH3 on bottom. And then we can go to moles of NO. Okay? So in this second step, right here, again, we use the molar mass. Nitrogen is 14. I'll work that out up here. So N equals 14, and we only have 1 of those. And then hydrogen, again, is 1, and we have 3 of those. So we get 17 grams of NH3 equals 1 mole. And then using our balanced equation, 4 moles of NH3 equal 4 moles of NO. Okay? And then let's make sure everything cancels. Grams of ammonia, moles of ammonia, and we get moles of NO, which is what we were looking for. So you'll work that out down here. Okay, let's move on to the next one. Oh, well, okay. I worked it out. Ding, ding, ding. There is your answer. Okay, so part B is the one that you have to work out next on your paper. So, again, the balanced equation was 4, 5, 4, 6. Okay? And so this is our given still. And our unknown is moles of H2O. So, let's start with 8. 24 grams of NH3. And if we have grams of NH3 on top, and what are we trying to get to? Moles of H2O. So we can't go from grams of NH3 to moles of H2. So we have to go to mole in H3. If we have that on top, we have that on bottom. And we're still trying to get to moles of H2O. So then we have mole H2O. Okay? The molar mass for ammonia is 17 grams in 1 mole. And then using our balanced equation, we have 4 moles of ammonia and 6 moles of water. Grams of ammonia cancel, moles of ammonia cancel, so that you just have to figure out how many moles of H2O there are. Okay, let's work out sample problem 9, where it says oxygen was discovered by Joseph Priestley in 1774 when he heated mercury 2 oxide to decompose it to form its constituent elements. So the elements that make it up. So first, let's figure out the chemical reaction for the decomposition of mercury oxide. So mercury oxide is, I'll go through it all with you. Mercury is Hg, and it tells us it's mercury 2, so we know it's 2 plus. And then oxide, or oxygen, is 2 minus. We crisscross and get HgO. That's mercury oxide, that's a G. Yields, so what are the 2 elements that make up mercury oxide? Mercury and oxygen, but can oxygen ever just be oxygen? No. So it's O2. So there's our basic equation, and then we have to balance it. And we have 2 oxygens on the product side, so we have to add a 2 here. And then we have 2 mercuries, so then we have to add a 2 here. And then it's balanced. Okay? So now let's look at just number 1 right now, and let's find our givens and unknowns. Our given is 125 grams of O2. And that's our given. And our unknown is moles of mercury oxide. Okay? So this is for number 1. We start with the given, 125 grams O2. If we have grams of O2 on top, we have grams of O2 on bottom. And we're trying to get to moles of mercury oxide. So then we go moles oxygen, moles oxygen, and then we can go moles HgO. Okay? So We know the conversion factor between moles and grams is the molar mass. So the molar mass of oxygen gas is 32, and that equals 1 mole. Always, the molar mass always equals 1 mole. And then we use the balanced equation to figure out 1 mole of oxygen gas equals 2 moles of mercury oxide. Grams of oxygen cancels, moles of oxygen cancels. We're left with moles mercury oxide, which is what we wanted. So you tell me the correct answer. For part 2, you'll also be working out. Again, we have the same given, but in this case, we have a different unknown. We want to know how many moles of mercury are produced. So we still have 125 grams of oxygen. Grams of oxygen on bottom. Moles of oxygen still. Moles of oxygen. But now we're trying to get to moles of mercury. Okay. So, again, 32 equals 1 mole of oxygen gas. 1 mole of oxygen gas equals 2 moles of mercury. So just by looking at the setup, it is the same numerical answer, just a different unit. Okay, make sure your units are right, but your number answer will be the same. Okay, on sample problem 10, it's taking it a step further, but we know how to do it. So it says tin 2 fluoride, which is SNF2, is used in some toothpastes, which you might be like, what? But fluoride is an additive in most toothpastes and most water because it prevents cavities. It is made by the reaction of tin with hydrogen fluoride according to the following equation. Okay, I give you the equation. Feeling nice? Let's make sure it's balanced. We have 1 tin, 2 hydrogens, and 2 fluorines. So it's balanced. So, got that taken care of. Now you have to identify our given and our unknown. It says how many grams of SNF2 are produced from the reaction of 30 grams of FH with SN. So here, this is the unknown because it's asking us how many, and it's giving us this, so that's our given. Okay? So as always, you'll start with your given, which was 30 grams. If you have grams of HF on top, you have grams of HF on bottom. We're trying to get to the mass of SNF2, so you have to go to moles of HF, moles of SNF2, then you have moles of SNF2, and then you can get to grams, using molar mass as a conversion right here and right here. Okay. So fill in those numbers. The molar mass of HF is 20. And get this from your balanced equation. You have 2 moles of HF for 1 mole of SNF2. And then your molar mass of SNF2 is 157.71 or 156.71 grams. For a total of 117 grams of SNF2 produced in the reaction. Okay? So on 11, you had to try that out yourself, where it talks about laughing gas, which is nitrous oxide, is sometimes used as an anesthetic in dentistry. It is produced when ammonium nitrate is decomposed according to the following reaction. Gave it to you. Let's make sure it's balanced. We have 2 ends. We have 2 ends. We have 4 hydrogens. We have 4 hydrogens. We have 3 oxygens. We have 1, 2, 3 oxygen. So it is balanced. Part A says, how many grams of NH4NO3 are required to produce 33 grams of NO2? So real life use of this, maybe, I am completely guessing, but they might need 33 grams of nitrous oxide to last through one dentistry procedure. So then they have to know how much of the reactants they need in order to produce that much product. Okay? But grams of NH4NO3 is your unknown because it's asking how many. And then 33 grams of NO2 is your given on number or letter A. Okay? So we start with our given, 33 grams NO2, or N2O. If we have grams N2O on top, we have that on bottom. We're trying to get to grams of NH4NO3. And you might be like, well, yeah, you can go from grams to grams, but there you can't. There's no conversion rate between grams of one compound and grams to another. There's no direct conversion rate. So you have to go then moles N2O, mole N2O, and then we're trying to get to NH4NO3. So then you go mole NH4NO3. If that's on top, it has to go on bottom. I'm running out of room. Okay. And then you can get grams NH4NO3. Okay. So right here, we use the molar mass of N2O as the conversion factor. Nitrogen is 14, and you have 2 of them, so that'd be 28, plus 16 oxygen, grams of oxygen, so that's 44 grams per 1 mole. And then right here, we use the balanced equation. So moles of N2 is 1. Moles of that is also 1. Yippee-ki-yay. And for every 1 mole of NH4NO3, now we have to work that out. Okay, so nitrogen, we have 2 total, and nitrogen is 14 grams times 2, 28. And then we have hydrogen, which is 1, but we have 4 of them, so that's 4. And then we have oxygen, which is 16, but we have 3, and that is 48, maybe? Yeah, 48. I did that in my head. Okay. Now you add all those together, and you get 80 grams in 1 mole. Okay? So then grams of N2O cancels, moles of N2O cancels, moles of NH4NO3 cancels, and you're left with grams of NH4O3, which was our unknown. So you can do the math. Make sure you're multiplying everything across the top. So in your calculator, literally put in 33 times 80, and then hit enter. And then take that number and divide it by 44. And then write that in the box and turn that in for me. Okay? Let's look at part B. But, okay, how am I going to do that? I'm just going to, we're going to do that. Okay. Just go along with it. I'm making room. Okay. Part B. Says, how many grams of water, that sounds like an unknown to me, are produced in this reaction? So we have the same given. So this is part B. And we have 33 grams of N2O. And if you have that on top, you have that on bottom. And we're trying to get to grams of water. And again, you might be like, well, wait, you have grams, so it just makes sense. They're both grams. So you can do them in the same step. No, because they're grams of two completely different compounds. So if you have 80 grams of one thing and 14 grams of another, clearly those do not equal each other, right? So you have to go next to moles N2O. And then if you have that on top, you have that on bottom. I hope we're getting the hang of this. And we're trying to get to grams of water. So then we go to moles of water. Moles of water down here. Ooh. And then finally, we have gotten to grams of water. Okay? So here and over here. Here, you will use the molar mass again, which we found in part A. So 44 grams of N2O equals 1 mole of N2O. Using the balanced equation, 1 mole of N2O equals 2 moles of H2O. And then 1 mole of H2O equals 18 grams, because 16 grams for oxygen plus 2 hydrogens equals 18. Okay? Make sure everything cancels. Moles, moles, moles H2O, moles H2O. So your answer is in grams H2O, but you, again, get to work it out. So work out parts A and B on that. Okay, sample problem 12, which you also have to write out. It says, and I didn't give you the equation for this one. Okay, it says when copper metal is added to silver nitrate in a solution, silver metal and copper 2 nitrate are produced. What is the mass of silver produced from 100 grams of copper? So first, let's get the equation. So it says when copper metal is added, so that means like copper's by itself, is added to silver nitrate, NO3, silver metal and copper nitrate are produced. We got a crisscross. Okay, great. Okay, and this is a lovely single replacement reaction, but it's still unbalanced. So to balance it, all we have to do is add a 2 right there and a 2 right here. Okay. So next it says what mass of silver. So what mass is the unknown is produced from 100 grams of copper. That's our given. Okay. So we start with our given. If we have that on top, guess what? We have that on bottom. We're trying to get to grams of silver, but again, we can't go from grams of one thing to grams of another. So we have to go to moles of copper. Moles of copper. And then we can go moles. What are we trying to get to? Silver. That's on top, that's on bottom. And we're trying to get to grams of silver. Okay, yay. Okay, the mass of copper is 63.5. If it's, if like the decimal place is small, like on hydrogen, I normally don't add it. But if it's, if it makes that big of a difference, if it's like over, 0.4 or whatever, then I will normally add it. But that equals 1 mole. And then here, we'll use the balanced equation. So for 1 mole of copper, we get 2 moles of silver. 1 mole of silver equals, we're rounding up to 108 grams. Let's make sure everything cancels. Grams of copper, moles of silver, and we're left with grams of silver, which is our unknown. And then you can calculate the answer. See, this part, like everything that we've been doing up until now, is kind of culminating here. So we have balanced equations. We have figured out chemical reactions based on like words and, things like that. So in order to help you get there, then when we were doing molar mass to help you get that, and then when we were doing molar conversions to help you get part of this, and then now calculating it. Okay? And here we are on the last problem that you will have to write. It says, what mass of aluminum is produced from the decomposition of 5 kilograms of aluminum oxide? Okay, so we have to write the equation. And it says the decomposition. So then we know we start off with Al2O3. And it decomposes into its constituents. So Al plus oxygen, but again, oxygen can't be by itself, so it's O2. And then to balance this, let's start with the oxygens first, because we have 3 oxygens on the reactant side and 2 on the product side. So we know we have to put a 3 there and a 2 over here. And then that gives us 4 aluminum. So there is our balanced equation. Okay, and this one might throw us off a little, or you might have completely, I might have even read it wrong. I don't remember, and I'm not going to scroll back to look. But it says our given, or let's do our unknown. Our unknown is the mass of aluminum. That's our unknown. And our given is 5 kilograms of aluminum oxide. Okay? And so you got to be careful with that, because it depends on what you're trying to figure out. The mass of aluminum could be in kilograms, but I'm going to do it in grams since that's what we've been working with. So kilograms, the prefix kilo means 1,000. So a kilogram is just 1,000 grams. Okay, that's why we like the metric system, because it makes sense. So if we have 5 kilograms, 1 kilogram equals 1,000 grams, then we get 5,000 grams. Okay, so I'm going to start with 5,000 grams of Al2O3 as our given. And then we have grams Al2O3. And then what are we trying to get to? Mass of aluminum. Again, we have to go moles Al2O3. Moles Al2O3. And then we have to get to moles of aluminum. Moles aluminum. And then you get grams of aluminum up there. Okay? So to find the molar mass of aluminum oxide, oxygen, as we know, is 16. Aluminum is 27. So aluminum equals 27 times 2 is 54. And then oxygen is 16 times 3 is 48. Added together is 102. 102 grams equals 1 mole. using our balanced equation over here, 2 moles of Al2O3 equals 4 moles of aluminum. 1 mole of aluminum equals 27 grams. Okay, so let's make sure everything cancels. Grams of Al2O3, moles of Al2O3, moles of aluminum, and then you're left with grams of aluminum, which is our unknown. And you can do the math. And just looking at the numbers, it will kind of be bigger since you already have on the top, you have 5,000 being multiplied by. So your answer is going to be bigger than a lot that we've worked with. Okay? So once you find the answers, once you've done the math on all these, take a picture of where you worked them out and answered them. Make sure the answers are in boxes with the units so that I can find them easier. And then simply take a picture and upload it into the assignment box on Google Classroom. I think that'll be easier than trying to make you type them out. That was probably a pain, and I think just writing it out and taking a picture of it will be easier. Make sure they're clearly numbered. Make sure the answers are boxed and you have your units on them with the answers, obviously. Like you should have been writing them in. Okay? For those 9 problems, sample problems, what were they? Sample problems 2, 3, 6, 7, 8, B, 9, 11, 12, and 13 are what you should have.